Good evening to all. We warmly welcome you to the next session of our Enigma 2024 workshop series. This will also be the last session of our workshop series, which mainly features about the power of mathematical skills in programming competitions. I'm Rahul Leela Ratne, and I will be your moderator for the today's session. Now, the time is awaiting, and the days are gradually approaching to the most awaited event, which is the Crack the Code Hackathon, which is exclusively open for all the undergraduates of University of Monaco. The registrations have opened now, and now I would like to make a small reminder to all of you participants to say that the registrations will close on the 12th of March, that is next Tuesday. So if you still haven't registered for the hackathon, please please register before the upcoming Tuesday, before the deadline. So today we have a very special guest speaker for the today's session. He who obtained first class honors in his bachelor's degree as an electronic and telecommunications engineer in University of Monaco. Now he works as a software engineer in one of the world's most prestigious companies, the Google company. Let's introduce our esteemed speaker, Mr. Nipuna Samarasekar. Mr. Nipuna, I pass the control to you. Excuse me, there's a small request from our participants. They say that they can't hear you. Your microphone is switched off, actually.
Hi, can you hear me now?
Yes, of course.
Okay, that's perfect. Sorry about the mishap at the beginning. Hello all. Good. I guess it's afternoon for you guys. Yeah, really nice to meet you all today. And thanks for the quick intro as well. Rahul, at the same time, could you monitor the chat? And if there's anything ongoing, like questions and such, could you just speak them out loud or ask them to mute and ask the questions themselves, if that's fine. Okay. Are you guys able to hear me yet? Or am I just talking to myself?
We can hear you. Well.
Okay. Yeah. Rahul, I was asking, like, if you can, please monitor the chat. And if there are any questions, please talk them out loud. Feel free to interrupt me. I want everyone participating to ask questions as and when they arise, so that we can answer the questions while we have the context. Yeah, thanks. All right, so today we are going to discuss about the relationship between mathematics and competitive programming. I'm aware that you guys have been learning a bit of Python throughout this series and also started looking into competitive programming. And I'm also aware that you guys have a strong math background. Most of you, if not all, have taken part in many competitions during your A-level times. And also, obviously, you guys did combined maths for A-levels, which kind of indicates that you guys already have a very strong mathematical background. So the idea of today's session is to translate your skill set that you already have into competitive programming and potentially incorporate new tools and tricks into your repertoire so that you can become world-class programming competitors. So before we begin, I also want to, let me really quickly start sharing the presentation as well. I hope you can see it. I can see that on the other screen. So I hope it's all good. So, okay, did I lose the presentation yet? Let me see. Maybe. Okay, sharing again. Yep. And for to all the participants, I want to tell you that if you have any questions, feel free to unmute yourself and ask. And if you're too shy to ask, or if you don't have a mic, or for whatever reason you cannot talk at the moment, feel free to type that in. Our moderator will kindly help us to monitor the chat and then escalate the questions. The reason why I want you to ask questions is that I want the session to be catering to your needs, not what I think you guys need. So definitely, if you have any questions, feel free to speak up. There's nothing to be afraid of. Everyone is on the same page. We all want to learn from each other and then grow. So don't worry at all. But like I said, if you don't feel like talking, feel free to utilize the chat. And also, as a result of asking questions, we might veer off into tangential topics, not discussing the content that I originally planned. That is completely fine. This is just one set of topics that I thought could be useful to discuss. But if you guys can think of better questions that needs to be answering, that, or you guys have other questions that you think could help others get started on the programming competitions and stuff like that, I think those are more important. So feel free to ask your questions. And if you get carried away, that's totally fine. And also, like, I'm sure most of you guys are solving interesting problems day to day because of the fact that you guys are already passionate about solving mathematical problems and also like want to take a step forward to take part in competitive programming contests. So if you have any interesting problems that you think others can learn from, or if you have been trying them for quite some time and you're stuck on those and you want to get yourself untangled a little bit or maybe try new ideas, we can discuss some of those because of the limited time. Depending on how much time we have at the end, we can discuss some of those. And I'm not guaranteeing you that we will be able to solve them, but we will make progress as a community and see where it goes. So if you recall some of the details, it's great. And if you don't, use the time during the presentation to try to get hold of all the information necessary so that you can post the problem articulately at the end of the meeting. So that is also something that I wanted to tell you. So if you are a pretty strong competitive programmer, and if you have like insanely difficult questions, they are also welcome. We might not be able to solve them, but we will be able to discuss some of the ideas and then collectively make progress. Okay, and yeah. Oh, I don't think you, okay, it's loading, so it's not too bad. Yeah. So when you actually look inside the competitive programming, what's behind the veil, what you really see is mathematics. And this is mostly true for many other subjects like physics and such. But if you look into competitive programming, it really is mathematics. Like there's nothing, I mean, there is programming, obviously. That is why they're called programming competitions. But if you take the programming aspect out of the way, it's all mathematics. And if you look deep enough into programming, you will also bump into a lot of mathematical ideas. And if you are really keen into learning the math behind programming, there are ideas such as like thinking of a computer program as a mathematical expression even. If you want to really pursue these ideas, I recommend that you guys can start learning a programming language such as Haskell. I'm aware that you guys have been using Python to learn programming. I'm mostly talking about the newcomers here. There might be seasoned programmers here, so please hold your horses until we get to the point that we can discuss interesting topics to you as well. Yep, and also it would be very nice if I can get feedback time to time, maybe in the form of asking a question or maybe a comment, so that I know that you guys can hear me and you guys can understand me. because sometimes it is possible that the line is not super clear, or there might be other reasons why you guys cannot follow along. So please let me know, give me some form of feedback so that I have an idea about what's going on. Okay, and also the other side of the relationship is mathematics benefiting from programming. That is also true. Most of the mathematical researchers these days, they utilize computers heavily. For example, like if you're trying to work with a newly known pattern and you want to sort of explore the lower ranges, lower behavior in the lower ranges of the numbers, you can just use a computer to quickly generate graphics and all sorts of things to visualize, so that you can develop even better or finer insights. So it is a two-way relationship. Obviously, programming stems from mathematics and also has benefited a lot from the core mathematical ideas. And similarly, mathematics is also benefiting from programming. There are some mathematical proofs which were solely based on computations. What comes to mind is, if you guys are aware, like the Rubik's Cube solution, if I recall correctly, any configuration could be solved using 21 steps or something like that. I don't exactly recall the lower bound. I think it's close to 20. The original proof was given using a bunch of computations. That is one of the examples where computers and programming was used effectively to produce a mathematical theorem, and that is only one of so many. And also, like there are other aspects of mathematicians using computers to solve their problems. There are automatic proof generators these days even, and with the recent rise in AI, it is likely that the AI assistants will start helping mathematicians to prove the smaller lemmas and stuff like that, also analyzing edge cases as well. So it's a two-way relationship. Even if you're not super interested into taking part in programming competitions, I still recommend you to learn a programming language. It's never going to hurt, even if you end up doing other things in life. Having a solid idea about a programming language and being able to produce at least a very basic script could go a long way. So let's move on. And yeah, I want to compare mathematics and programming side by side, and specifically not only the programming, but the competitive programming aspect of it. So the fundamental similarity in both of these things is that you need to be very creative. You need to be able to come up with new ideas based on your existing knowledge to solve difficult problems. And also, like some of the ideas that are used in mathematics, mostly from graph theory, number theory, and combinatorics, they are very frequently employed in programming challenges. And also, if you look into most of the common algorithms that we use to solve day-to-day problems in programming, like the search algorithms, graph search, obviously, and there is a bunch of like prime generation algorithms which are required for cryptography and such. Most of these things are exact translations of the mathematical ideas into a programming language. So that is also another strong reason why you need to have a strong mathematical background in order to be a great programmer. And then moving on to the next slide, and logical thinking and reasoning basically along the same line as before. You need to be able to build on the facts you already know. Even in a competitive programming environment, the process is very similar to solving a math problem. You just go through the problem statement, and then you try to identify the logical connections between the components in the question, and you start building up from there. So it is exactly the same process as solving a math problem, right? You try to work with the given set of information and then try to derive more and more connections until you get to the point where you arrive at the intended result. So in that way, like a mathematical proof and coming up with working and accurate solution to a programming problem is very similar, because even in programming, you should not just try out all the algorithms you know on a problem to see if they work. Instead, you should be constructing an algorithm or finding a similarity between an algorithm known to you and the problem that you're trying to deal with, and you need to sort of prove the correctness of the algorithm. Sometimes it may not be trivial to prove it, but at least like it should be quickly verifiable conjecture, I would say, before you start like implementing code. So when you're taking part in programming contests, when you try to solve problems, there is a couple of steps before you get into any coding at all. First of all, like you need to understand the problem by reading it carefully and then try to come up with a solution. Sometimes even the problem itself tells you what to do. So you might be thinking this is very straightforward. I just need to exactly write a code that does what needs to be done, what is being told. But I think there's an additional step. You need to understand the time complexity and space complexity of the exact implementation, like the naive implementation. What we call as naive implementation is basically translating the problem statement into a code. And they might work like during the very basic level or the initial level. Whenever you start solving from relatively easier set of problems, and then you gradually level up the difficulty of the problems, right? So when you start off, most of the problems, for most of the problems, this naive approach would work. Basically, like you just need to read the statement and then write a code which does exactly what it says. But as you progress through the difficulty ratings, what's going to happen is that these naive programs would turn out to be too slow. Then another aspect of mathematics comes into play. You need to be able to understand the time complexity of your solution. Basically, it is an estimate in terms of the size of the inputs to understand how long the program would take to execute if you just implement the problem statement as is. And most of the time, it turns out to be that it's going to be a number of years or maybe even decades before the program will result in anything, which is not practical. Then you move on to the next step, that is the optimization. Basically, like you try to translate the problem into a simpler form to make sure that it can be programmed in a way that results in the final intended output in a limited amount of time. So there are multiple ways to do it. Firstly, like you can try to use your mathematics knowledge alone to translate the problem statement into an isomorphic, but computationally relatively simpler problem. And then there are like programming techniques such as dynamic programming, recursion, and then like there are all sorts of things that you will bump into soon. You can utilize these techniques to bring down some of the aspects of the time complexity. For an example, like there are common ideas which can bring linear time into logarithmic time and such. So you will understand more once you have a clear idea of what time complexity is. If you don't already have an idea, I highly recommend you read up on it, try to understand what time complexity is, and try to estimate the runtime of your programs in advance rather than like actually implementing everything and then running it and learning that it's too slow. And that is not going to work in programming competitions, because then your competitors might be using that time effectively to solve another problem while you were coding away a very slow program to ultimately produce an unworking solution, because even if it works, it's too slow. So you will not be able to get the answer within the duration of the contest. So yeah, definitely try to understand the fundamentals behind time complexity analysis. That too would require you to have a strong math background. It's basically a counting problem. You're trying to count how many iterations a particular program would take before it produces the result. And we typically try to use the worst case of the input to estimate the time. That way you are sure that even if you bump into the worst case, your program should terminate within the given time. And also, like for some of the programming competitions, they also want the solution to be fast enough so that it executes within a given time. So basically, like you need to upload your source code, and it will be executed on the competitive programming platform servers. And then if it runs within a certain time limit, you will get it as an accepted solution. If it is too slow, you will not get any points. You would need to optimize it further to get any points for the problem. So having a deep understanding of the time complexity is super critical. Okay, I also mentioned that some of the ideas in programming are actually stemming from mathematics. So I want to give you an example. A couple of things out of the couple of things that comes to mind. One of the interesting ideas in programming is recursion. So recursion is essentially like we try to break down the problem into a very similar problem, but with smaller inputs. Basically, like let's say, like you're trying to find the nth Fibonacci number, and the easiest way to break it down to two smaller pieces would be to express it as a sum of the two preceding Fibonacci numbers, right? So if you, for an example, if you're trying to find the 10th Fibonacci number, instead you can just find the 9th and 8th one and produce the 10th one by summing them together. And then you can repetitively apply the same thing, basically like you apply the same thing to Fibonacci 9 and express it in terms of 8 and 7. And you go on until you reach the base case, which is like Fibonacci 0 and Fibonacci 1, right? This fundamentally is very similar to mathematical induction. Mathematical induction is sort of building from ground up. You start off from a very small set of numbers, and then you continue to use those results to prove that the same result holds for larger numbers. Sometimes it could go up to infinity even. So, and the recursion, in a sense, feels like the reverse process. Basically, you start off with a larger number, and then you keep breaking it down into pieces until you reach very small pieces that you can solve trivially, right? So if you compare these things, both of these are iterative processes, and the fundamental structure is more or less the same. Basically, like you start solving by very basic trivial problems, and then you combine them together to produce more and more complex results until you are able to compute something super complex. So that is one of the examples where ideas from mathematics are translated into programming to be used as a very effective tool to crack really hard programming problems. Yep. Yeah, I think another interesting detail is that even the mathematical problems, they have varying. I think we briefly touched about the space and time complexities previously, but there is another aspect. So regarding the problem difficulty, even for the math problems, if you have been solving problems for quite some time, you should understand that there's a range of difficulties from like very easy to complex. And the complex ones are complex because it could be multiple reasons. Most common reason is that it requires multiple, I would say, crux moves. Crux move is basically the key move that you feel like you made a lot of progress towards the solution intuitively. But some of the problems, like if they are really difficult problems, they may have not only a single crux move, but multiple of them, which makes them relatively difficult because you are not sure whether you are along the right path or you just obtained a result that is completely useless, right? So that sort of requires you to have much deeper insights about the problem that you're solving rather than like just coming up with intermediate results. The path that you are moving from your like given set of data to the ultimate expected final value needs to be guided. It could be based on your prior experience, or it could be based on the input data as well. So this requires you to understand the subtleties behind the actual mathematical theorems. For an example, like if you know Fermat's Little theorem, it is just a mathematical statement, right? If you don't understand the actual essence of it, you will not be able to utilize it to solve a problem. So some of these like theorems feature more advanced ideas compared to the other ones. For an example, a more familiar theorem would be a Pythagoras theorem, which most of us use very effectively. I think that is mostly because of practice, because if you really look into it, it's not super trivial what the fundamental idea behind Pythagoras theorem is. right? But as opposed, like if you just sometimes we utilize the fact that square of a real number, or yes, like let's not think about the imaginary parts of the numbers for now. So let's say like a square of a positive number or a negative number is always a square. That idea is super simple. Anyone who's familiar with arithmetic knows the idea. So even if they don't know about the theorem itself, I wouldn't even call it a theorem because it's super straightforward. But even if they don't know the result, they can easily derive it because they have the idea in their mind. We all understand that a multiplication of a number by itself will produce a positive or zero value, right? Similarly, it's the same is not true for Pythagoras theorem. For an exercise, you guys can try to find the idea inside the Pythagoras theorem. Obviously, we all know that, but let's assume if you didn't know that, would you be able to use the same idea to solve a problem? Some of you might be able to use it, some of you may not be able to use it. That is the exact point I'm trying to get. It's more important to grasp the idea inside so that you can utilize that in other places, even when you don't know about the theorems in that domain. So otherwise, something that usually happens is that whenever you start on something new, you start to think that I do not have enough background knowledge to even begin solving problems. But if you have this like ability to transfer your knowledge from one domain to another, then you don't need to worry too much about your background knowledge. Obviously, you need to improve the tools in your repertoire and build your background as you progress, but it will give you a nice stepping stone that you can start working on the problems immediately, even before learning anything in the new domain. So yeah, these ideas of like the problem difficulties and the difficulty of the ideas behind mathematical theorems, they translate really well into like algorithms that we use. Like there are algorithms which feature really simple ideas. For example, like DFS, BFS, they have relatively simpler ideas. And there are algorithms which feature very complex ideas. Or maybe it is possible that it is a collection of simple ideas or very complex idea. So this idea of difficulty is also transferable between mathematics and programming. All right, another important thing in the world of programming is data structures. This is not something we typically encounter in mathematics, but that statement isn't exactly true. Even in mathematics, we try to utilize matrices, for example, to store the data that we want to process, and then we use matrix operations to transform them into other like forms efficiently. And also like in graph theory, in mathematics, we also utilize like graphs to represent structures and then use graph algorithms to arrive at different results about the structure that we are trying to deal with. So data structures in programming languages, they also mimic these ideas. They typically represent a mathematical object, and you can apply different transformations into that. And data structures are classified based on how efficient they are at applying different transformations. So this is also a necessary tool for all of you to have in your repertoire. You guys need to know which data structures are better at what, so that you can utilize them efficiently. And in order to have deeper insights into how data structures work, once again, you need a strong math background, because these structures are mostly mathematical, and the time complexities you get out of them are typically proven using mathematical ideas. So once again, like you cannot do really well if you don't have a strong mathematical background. All right, I think we've been talking for quite some time. So let's take some time to think about a problem and try to sort of walk through how to solve the problem, which will help you to understand how to translate your mathematical ideas into code to solve difficult problems. I think this problem is moderately difficult. For a starting programmer, this problem might be super difficult. And if you have a strong math background, you might find this easy. So please bear with me. And I want to take a brief pause here and see if. Oh yeah, I see a question in the chat, but yeah, I'm gonna take a brief pause while you guys can digest the problem statement and take some questions if you have any. Someone is asking what are the benefits for our career if we participate in hackathons. I can speak about programming competitions. There are various forms of hackathons. So I hear someone's mic going on, but yeah. I hear someone's mic. Please, yeah, try to mute yourself if you think your mic is producing the noise. Thanks. And yeah, talking about career benefits that are stemming from programming competitions, one of the key things that I want to highlight is that most of the companies they try to find generalist software engineers. What they mean by that is programmers who are good at most of the programming tasks, not doing very well on a specific. They might be also doing very well on a particular area. But for an example, Google Summer of Code, I can try. Can you hear me? Okay.
Okay, sir. Yeah.
Yeah. So it seems like I ended up muting myself in the process. Yeah. I'm not sure when I was muted. I hope you were able to hear some of the blabbering that I was doing so far. Yeah, again, coming back to the career and participation in hackathons, I was saying that I can speak about the programming competitions, but not about other hackathons because I am not super familiar with them. Programming competitions will definitely help you because most of the top software companies they try to hire generalist software engineers, basically meaning software engineers who can learn new skills really fast and then effectively use them in their day-to-day jobs. So the way to filter out that generalist software engineers is this is the generally accepted standard. There might be other ways. What we typically do, at least at Google, is that we try to feature algorithm problems in the interviews and measure the candidates' strength based on their performance on these algorithmic problems. So what you get out of taking part in programming competitions is that this is more like practice in advance. You guys may have heard about Lead Code and other platforms as such, which folks use to practice for interviews. So typically what happens is that most of the folks graduate and then they start looking for jobs and then they realize that they need to have good programming, programming problem solving skills for them to perform well at the interviews. So then only they will start learning these material and then start practicing. But I believe then it is a bit too late because you are already looking for a job and you are also dealing with a lot of other things. So you will not have enough time to put into these things, as opposed to like if you were an avid programming competition participant, then you've already been doing this for multiple years and you are super familiar with the domain, and you probably have acquired a lot of skills by the time you actually go into the interview. So this is more like a practice well in advance. And then another secret is that the questions that are used in interviews are much simpler than the most difficult problems that are used in programming competitions, which means like if you are consistently performing well and solving hard problems in the programming competitions, the interviews should be a walk in the park for you. So basically, like once you get the interview, if you are going for an entry-level job, then it is more or less guaranteed that you will get the job. Once again, I think, yep. Sorry about that. I think if I hear background noise and if someone is not planning to ask a question, I'm going to mute them. But if you are going to ask a question, please unmute and speak up. All right. I think someone asked about the Google Summer of Code. I think it would be better if you guys can just like go. Hi, I hope you guys can hear me again. Yeah, I think this is starting to become a bit painful. Let's try to figure out what's going on. Okay, yeah, I hope you guys can hear me. And please let me know in the chat if you cannot hear me, because otherwise I would not know whether you guys can hear me or not. Okay. Okay, that's nice. Yeah, I was talking about Google Summer of Code. I wasn't really saying anything about Google Summer of Code. I was basically asking you guys to just do an online search and try to get more information as possible. There is a process that you can apply for projects, and then if you get selected, you can work with a company. Typically, that is mostly the outline of the process. There are some intricacies, and I haven't personally taken part in Google Summer of Code, so I don't know any additional details about it. So I cannot give you more information than what you can find online. So yeah, and also like I guess looking at the chat, we don't have any more additional questions, or do we? Oh no, it seems not. So let's try to make progress in today's topic if we can. Okay, so I hope you are able to read the problem statement, and I also want you to focus on some of the key details here. So I'm pretty sure you guys may have come across Fibonacci numbers at this point. Fibonacci numbers is essentially the numbers that starts at 0 and 1, and then you obtain the next term by adding the two previous terms together. So you can keep doing this towards like very large numbers. And an interesting observation is that the numbers are always increasing, because like these are after the second term, these are positive numbers that you are adding up, which means the result is going to grow. And if you're interested in finding an upper bound, a trivial upper bound would be 2 to the power n, because every time like adding the two previous terms, which means there's zero chance that you will end up with a number that is more than twice as large as the previous number. So that 2 to the power n would be a trivial upper bound. Sorry, but I think if you understand how large 2 to the power n can grow as n increases, you can easily see that these numbers won't even fit in memory once you go past, let's say, 10,000, right? I mean, a single number could potentially be in the memory, but you will not be able to work with a bunch of these numbers by putting everything in memory. So another interesting detail when you are going through a problem statement is the size of the problem. And if you look at this particular problem, this problem defines the Fibonacci numbers that is already known to us. And then they also define a polynomial of, let's say, like Fibonacci polynomial. Essentially, what it means is that the polynomial, I'm assuming that you guys know what a polynomial is. You can even call it a function if you are not too familiar with the idea of a polynomial. Basically, like for a function, you just put in an input value, and then it will give you an output value by applying some operations into the input value, right? So this Fibonacci polynomial is defined in a way that it is a function of the input, the increasing powers of input, and each power of the input is multiplied by the corresponding Fibonacci number. If you notice, like this is the Fibonacci function 7, and it is including 8 different terms starting with F0 from 0 to 7. That is where 8 is coming from. And for each term, the power of the input is multiplied by the corresponding Fibonacci number. This is actually, 7 terms, because F0 is 0, that term cancels out. So you don't need to really write it down. So this is like F1 multiplied by X, F2 multiplied by X squared, all the way until F7 multiplied by X to the power 7. So what would be your initial observations? And we were talking about the limits. So let me come back to that. And then the objective of the problem is to find a summation of these functions for several input values. And the input values are reasonably small, from x equals to 0 to x equals to 100. And we all see that when x is 0, this becomes 0. So you can even like get rid of the x equals 0 and start from x equals 1 to 100. And this range is relatively small. That is one of the observations. And the other one is n is 10 to the power 15, which is like, if you really try to understand, the function fn would have 10 to the power 15 terms, right? And each would be of the same form, like Fibonacci of n multiplied by the corresponding power of x, right? So if you really like look into this function and implement it as it is, computation of this function would take x times n operations, because for each x you need to sum n different terms. And to be precise, it could be more than n, because to compute each one of these n terms, you also need to do additional operations. But even if you could just like compute everything in constant time, it's going to be n times x, which is 10 to the power 17. And another key detail, that they are only asking for an answer modulo something. If you are not familiar with the idea of modulo is the remainder that you get when you divide a number from this number. So this is helpful, definitely. This means that you will be able to work with the remainders. You don't need to compute the actual numbers. For an example, like if you try to compute the Fibonacci of n for n equals 10 to the power 15, it is going to have a very large number of digits, right? Typically, like number of digits is approximately equal to n divided by 3, something like that. And the interesting observation is that you don't need to have the full number. You can only work with the remainders. So you can just compute the remainder modulo this number, let's call it mod, and work with those numbers instead of actually computing the numbers. Okay, so let's try to start off with the naive implementation. I think we briefly discussed that. Naive implementation is the exact implementation of the problem statement. If we do that, it's going to need 10 to the power 17 to compute this summation. And also for each term, right, you would need to compute the Fibonacci of that term and the power of x for that term as well. That is also going to be non-trivial. Basically, like computation of the Fibonacci n would also take n operations, because you would need to start from 0 and 1 and then continuously build up until you get to the n. But if you're computing all of them at once, that means you can compute all of them in O n operations. Similarly, for the powers of x, you can continuously multiply x by itself to produce all the powers of x in n operations. So basically, the time complexity would be n times x, and that is 10 to the power 17. If you are familiar with modern computers, most of the personal computers, they can run from about 100 million to 1 billion operations in a second, basically 10 to the power 8 to 10 to the power 9. And if you are to execute 10 to the power 17 operations, you should be able to compute how long it's going to take, right? If you can only run 10 to the power, let's say 9 on a super fast computer, you would need 10 to the power 8 seconds, which is a very long time, and it is only to just compute a function. Too much computational power wasted, so we definitely don't want to do that. And we understand at this point that we cannot just do the naive implementation and then find the solution to the problem. So then the second step comes in. The second step is that you need to use your mathematical knowledge to try and translate this problem into something simpler. And given that the audience today is relatively new, I'm not going to assume that they are all going to have the required background. So I'm going to explain, build up a little bit of background before we actually go into solving the problem. And then we will use the newly built background to solve the problem. Okay, so first things first, let's try to find a fast way to multiply a number and obtain a power. So if you notice, if we go back to the problem statement, in order to compute the function, like let's not worry about the summation yet. We want to be able to sum 100 different terms when x values change. But let's think about a single x value first. And when you, let's say, like we are trying to find x equals 10 here, and when you want to do that, you at least need to have a faster. You need to have a faster way of computing all the, let's say, a single term. Let's only focus on a single term, the last term. You need to be, and not that in our case, this is not f7, this is f of the function for the 10 to the power 15, right? So if you notice, this polynomial would have 10 to the power 15 terms, which is a massive number. And to compute that, you would at least need to be able to compute if you think of the last term, you would need to compute the Fibonacci 10 to the power 15 and the x 10 to the power 15 power of 10 to the power 15 power of x as well. So these two in itself are supermassive computations, right? If you just multiply x by itself 10 to the power 15 times, it's also going to take a long time, and you might not be able to get the answer until you let the program run for a couple of days, right? Or maybe even more, right? So we want to start off by finding two means to compute the power of a number efficiently. And similarly, we want to be able to find an efficient way to compute the Fibonacci numbers. And then note that we don't need to exactly compute the full values. We just want the remainder when they are divided by this particular mod value, right? So our first focus is trying and finding effective mechanisms of computing these two individual terms, right, efficiently. So first thing is that we try to find the a to the power n efficiently. In mathematics, like we typically refer to it as exponentiation, meaning that n is the exponent. So we want to be able to like exponentiate a number very fast. So if you do this naively, you just multiply a by itself n times, which is going to consume n operations. But there is a faster approach to do that. Basically, this is again recursion. So we try to find the power n, and if n is even, you just need to find the half power and then multiply it by itself. So basically, like we are spending a single operation to bring down the power by 2, right? And if the power is odd, we just need to make it even by taking one a out. We just spend a single operation to make it even. So basically, like these first two is going to happen until we reach the base case where we reach the 0th power, which is 1, a non-result. So if you notice, we were able to reduce the power by half by spending at most 2 operations, which means like every time you do 2 operations, the power that we need to compute is half. And if you spend a little bit of time understanding the number of iterations required to compute the full number, it is going to be log base 2n, right? Which is much faster than n. If you want to compare these two, for n around 1000, log base 2n would be around 10, right? So super fast as n grows. And going back to the original problem, for 10 to the power 15, log base 2n would be, I think, something like around 50, which is much more smaller, right? N equals 50, the program will run in a flash in a couple of milliseconds. And I also have, like, since you guys are familiar with Python, I have two Python implementations. One is the exact. So if you notice, once you're familiar with the language, you can translate these ideas very easily into programs. This particular idea is translated into code in just a few lines. You see, like, exponent equals 0 is the base case. And if exponent is divisible by 2, we just try to find the half power and then multiply it by itself. And then also notice the mod value, right? Because in the problem, we are not interested in the exact value of the result, but instead the remainder when divided by the mod. And if the power is odd, we just take one out to make it even, right? An interesting observation is that we can extend the same idea to matrices as well, which is something that we'll use in the problem that we are dealing with today. So it's essentially the same. Let's say, like, you already have a matrix multiplication implemented. Matrix multiplication, if you're not familiar, you can look up. It's going to be a n cube operation. Basically, like, there will be this multiplication specifically assumes that a and b. This multiplication doesn't, but in order to find a power of a matrix, the main requirement is that the matrix should have the same height as width, right? Otherwise, like, you cannot multiply it by itself. So matrix multiplication is n cube, and it's relatively trivial. Like, we basically, like, do what's being basically write the definition in a programming language would give you n cube. There are obviously ways to optimize that. There are some optimization tricks which will give you time complexity somewhere around n to the power 2.7. But if we don't do that, we would still get like n cube. But if the metrics are small, then it could be an effective algorithm. But if the metrics are large, then again, n cube is pretty large, so it will not be super useful. Let's say, like, similar to multiplying the numbers, you already have the matrix multiplication implemented, and then finding a power of a matrix is exactly the same as finding a power of just a natural number. So similar to what we did previously, if the exponent is 1, we return the matrix itself. If the exponent is divisible by 2, we just find the half power of the matrix and then multiply the half power by itself to produce the full number. And if the power is not even, we just take 1 out to make it even. Hope that's clear. Do you guys have any questions about this so far? I see someone is connecting to audio and then went back to mute. So yeah, I assume that no questions so far.
If you have any questions, ask it from sir or put it in the chat. You can also unmute and ask.
Yep, that should also work. All right, so now that we understood the fast exponentiation, we know how to compute a number, the power of a number very efficiently, only spending log n operations. And then coming back to the Fibonacci sequence, because the other requirement of the problem is that you need to be able to compute the Fibonacci n term in the Fibonacci sequence efficiently as well. And similar to the exponentiation, if you do it naively by just adding the previous terms, it's going to take n operations, and it is not feasible in our case because n is super large. So we want to be able to compute that more efficiently. All right, we will try to utilize another tool we have in mathematics, that is the matrix multiplication, which we briefly touched because we already know that you can multiply matrices similar to a natural number using log n times the matrix size, side length, or size cubed. So we try to express the Fibonacci relation in terms of matrices. If you notice, like, if you just have a column vector or a column matrix, which has 2 adjacent terms of Fibonacci, you can just multiply it by a very simple matrix to bump up the numbers by 1, right? If you notice, what's going to happen here is that first row is going to be multiplied by this column, resulting in fn minus 1 plus fn minus 2, which is the next term in Fibonacci. And the second row in the column is produced by multiplying the second row of the input by the previous Fibonacci terms. And you notice that the second value is 0, so it's just going to be 1 times fn minus 1, which produces this. So while this is very trivial, this is where the creativity comes into play, right? Once we can extract, like express the same relationship in the form of a matrix, what's interesting is that you can recursively apply it to like push down the right-hand side Fibonacci values even further. Let's say like we start off with this, and then we try to apply the same thing to fn minus 1 and fn minus 2. We can represent that as the same matrix multiplied by the fn minus 2 and fn minus 3. So we can keep producing the multiplications until like we reach f1 and f0, and we already know f1 and f0. F0 is 0 and f1 is 1. So we essentially like boil the fn down to this, right? So this relationship will give you fn by multiplying a bunch of matrices. Like this is still n is super high, right? In our case, 10 to the power 15, but this piece is super trivial. It is just 1 and 0, right? So you understand that if you can find the nth power of this matrix, you can find fn in a very straightforward manner. So we already discussed the fast exponentiation. We can compute this very efficiently in log n terms. In our case, log n, we estimated that to be around 50, right? When log is around 10 to the power 15, which means, and also the side length of the matrix is very small, right? Side length is 2, which means multiplying 2 matrices is only going to consume 8 operations. And which means you can compute this value very efficiently by only spending 50 operations, or 50 times 8, because matrix multiplication is 8 operations, right? So in terms of like computational complexity, 400 operations is super fast, because we know that a modest computer is able to iterate like 10 to the power 8 times in a second. So this is going to be like super fast again. All right, now we have a way to compute the Fibonacci numbers very efficiently. And another interesting detail is that for all these intermediate steps, we are only computing the modulo value, because if we just compute the absolute values, these numbers are going to grow massively. And when the numbers become super large, even multiplying them will become too slow. So it is not, this is not feasible if you want to compute the exact values. These relationships are still correct, but when you try to do that, your computer will become slow and slow, and then at one point it's going to run out of memory because the numbers are becoming too large. So while this works, keep in mind that Fibonacci numbers grow very fast, so you will not be able to store everything in the memory. And typically, like if someone is asking for very, very large Fibonacci numbers, they will ask for a modulo remainder, because asking for the complete value is not feasible. So now we know how to compute the Fibonacci of n, and we also know how to compute the power of x. So I think we have all the fundamental pieces here, right? We can compute fi efficiently in log n operations, xi efficiently in log n operations. But then again, like in order to compute the full function, you would still need to sum n terms, right? N is from 0 to 10 to the power 15. Even just summing terms, if you have to sum that many terms, it's going to slow down, right? Because you're only able to do 10 to the power 8 or 10 to the power 9 operations in a second. So now you need a bit of creativity to transform this into something more simpler. And what are we going to do? So we are again going to utilize the mathematical tools that we use to deal with the functions to come up with a more simpler expression for f of n. What we are going to do is we are going to utilize the Fibonacci relationship again. we are going to multiply so this is the function that we have, like the capital F of Fn of x. So we are going to multiply the function by x and x squared and then subtract from the original form. The idea of like multiplying by x and x squared is to bring the two preceding terms to the same exponent of x, basically like resulting in terms like this, right? F3 minus F2, F1. And the idea behind that is we know that F3 is equal to the summation of the preceding term, so that these terms will cancel out, right? So this is going to happen all the way. There's more to the equation that is not written, and a very large number of terms are going to cancel out, and only the first and last few terms will be remaining at the end. So this is going to give you an expression like f1 multiplied by this will be equal to the numerator that you have here, and then when you divide both sides by the negative of x squared plus negative of basically x squared plus x minus 1, you express the function in relatively simple terms, and you no longer have a summation here. It's just Fibonacci number multiplied by a large power, Fibonacci number multiplied by a large power. X is super trivial for a single x, like you know what x is, and x squared plus x minus 1 is again super trivial, right? And we know that Fibonacci numbers can be computed in log n. X to the power n can be computed in log n, similar for these as well, which means the numerator can be computed in log n, the denominator can be computed super efficiently in near constant time, right? It's just squaring x and adding x minus 1. So now we have a way of computing the function very efficiently, and it's just a matter of adding the values for x equals 0 to x equals 100, which is going to consume 100 operations. So the time complexity we have now is 100 times log of n. Log of n is around 50, we estimated it to be. And overall, it's going to be 5 times 10 to the power 3 plus some multiplier, which is not super large, which is clearly under 1 second. So computation of this can now fit in under 1 second. All right, there is a little bit of details here. In the problem, they're asking for the remainder, basically the modulo number, this number modulo the given mod value, this value, right? So for addition and multiplication, you can apply mod whenever to the intermediate results, and the final summation would still give you the same result. Basically, like it doesn't matter when you apply the modulo operation before multiplication or after multiplication, you would still arrive at the same thing. Same is true for addition as well. But for division, it is not true. That is what I have written here. So you want to be able to compute the modulo for the division. That's a bit tricky. If we just do like modulo separately and then divide them, you're not going to arrive at the right answer. You would need a little bit of a number theory background to understand that this is not accurate. I mean, you will understand this is not accurate by just plugging in some numbers, but in order to make sure that you come up with a way to make sure that you compute this accurately, you need a bit of number theory. So there is a relatively standard trick that you can use in the cases where A is divisible by B, basically like A is a multiple of B, then you can compute the same mod value using this. And there is a more expensive alternative as well. There is this theorem called Chinese remainder theorem, basically breaks down M into its prime components and then computing the remainders for those prime components and then consolidating them together to compute modulo M, which is relatively more experienced, so I'm relatively more expensive. So I'm not going to go into details. So instead, we are going to just use this, and this is like very straightforward. Instead of taking modulo M, we would need to take modulo MB, and then we divide the result by B. This is very easy to prove. You can do it as an exercise. And then now we have like all the pieces. It's just a matter of combining everything together to produce the answer. So we have the fast matrix multiplication, which we previously looked at. And using that, we can compute the, sorry, matrix multiplication in itself is not fast. I should not call it fast because it's n cube. It's slow actually. But the matrix size is very small. It's 2 by 2 matrix, the matrices that we are dealing with. And matrix power is the fast exponentiation we discussed. Like you can compute the power p in log p time complexity. And using those two, we compute the Fibonacci of n by using the relationship we just looked into, right? So that is also like, if you look into the fine details for a given n, we are computing the matrix power n minus 1, which is log n. So this function will also be log n, right? And then we know how to get the power of a natural number. That is again fast exponentiation we discussed, that is going to consume log n. So far all the operations we discussed are log n operations. And then this is the function value n fn x modulo m, right? We are basically like computing the same things that we discussed before, right? Using this definition of the function, which is much simpler, not the original summation. We identify this as a and this as b, and then just compute the a divided by b mod m. So it's relatively straightforward. This is b, sorry. And the Fibonacci n would give you the two terms of the Fibonacci. Sorry, I think this one has an additional output, so disregard this one, just use the first value. You would get the Fibonacci number, fn, and then it's a matter of like finding this division, right? It's basically a modulo m times b divided by b. This is truncated a little bit, don't worry too much. It's the same thing that is expressed here. And after that, you divide the result by b, basically like this operation here, right? And then you have expressed the fn. And then you just need to sum everything from 0 to 100, right? That is what we are doing here. X range is actually 100 here. And yeah, that's it. So it is at the very first, like if you look at the outlook of the problem, it feels like it's a very complex problem. But when you actually break it down into pieces and then use your background knowledge to address each piece where the complexity is coming from, you will be able to arrive at a really nice solution. And the first thing that you need to understand is that there is a problem. If you try to do it in the naive way, it is not going to be fast enough. Once you understand that, you try to optimize each components using your mathematical knowledge, and then you use mathematical creativity to further simplify it. And once you apply all of these things, it translates back into a relatively simple code that you can write in the manner of minutes, right? So that is how you solve hard problems using your mathematical background effectively. You don't need to be a programming pro to do this. If you have a strong mathematical background and a basic understanding of a programming language like Python, that alone is good enough, and you can solve a very large range of problems using that. So I hope the hands-on experience we just had is a testament to what I was saying all along. Basically, if you're very strong at math, and if you are able to solve very difficult math problems, then it's just a matter of learning a simple language, programming language, before you become a world-class competitive programmer. So yeah, having said that, I think that is the content that I wanted to discuss today. So at the beginning of the session, I mentioned that if you have any problems, interesting problems, or problems that stumped you, we can discuss them at the end. And now would be the time to ask questions about the content that we discussed today, plus anything additional that you have in your mind, any problems or any domain, any problems in the domain, hopefully. Like for an example, if you want some tips and tricks about different areas in programming competitions, I can also provide some guidance here. So please ask questions if you have any. Yep, I'm gonna wait a couple of minutes to see if anyone has any problems, interesting problems that they are willing to discuss, or if they have any questions. If not, I think yeah, it's a wrap.
So now the discussion session has begun. So please clarify all your doubts from sir. Now this is the time to get clarify the follow questions. So please use that time wisely. You can unmute the questions and ask, or you can put them in the chat.
All right, I think the wise use of time seems to be not asking questions. That's perfectly fine. I assume that you guys were able to understand everything we discussed today, and I can also share the slides if someone is interested. Please let the organizers know, and I'm happy to do that. And I hope you're able to take something out of it. Given that we don't have any questions, I wish you good luck. Oh yeah,
Says
that's
me.
great. So yeah, we
Sir,
seem to have a question.
yeah, they have posted some questions.
Yep. Yeah, I see some of them in the chat, but some of the questions, they just seem to pop up and then go away. So I lost track of some of them. Virosha, do you have access to the questions that they ask? Or maybe I can load the chat from somewhere else. Okay. Oh yeah, I can see them now. Yep, great questions. Yeah, can you explain why x to the power n computations, okay, become log n? Let me take a step at it. Let's see. I can just write down here. Okay, we can walk through. I think I need to move to a different window so that you will see the properly oriented version of me. Yes, nice question. So basically, like trying to better understand how the computation of. Let's go back to the fast exponentiation slide, if we can. Yep, essentially like. Okay, so we want to understand why this is fast. It is typically clear, like when you try to find the power of n of something by multiplying itself n times, right? It's going to take you n operations. I assume that is clear. And what we are going to do today is what we have already discussed, but let's go into a little bit more details. Let's pick an actual power. Let's say I want to compute the, let me pick something not too large so that we can work out the details. Yep. Let's pick 33 instead. Yeah. Okay. And if you do this using the typical implementation, it's going to require you to multiply 3 by itself 33 times, right? So if you use the fast exponentiation algorithm that we discussed, what we can do is that if we just repetitively apply that, we just break it down into 3 times 3 to the power 32, right? This is still a single operation. And then instead of computing 3 to the power 32, right, I am going to write it as 3 to the power 16 times squared, right? And then I also understand that 3 to the power 16 can be written as 3 to the power 8 squared. And then we also need to take the square of that as well, right? And we understand that squaring is just multiplying by itself. So if we keep applying the same thing, this is going to look like something like this, right? So we just repetitively take the squaring by itself. We can just compute this value by only spending 5 operations. Basically, like we multiply 3 by itself, which will give us 9, and then 9 by itself, which will give us 81, right? And then yeah, we keep doing the same. Like, sorry, this is like 9, 3 by itself, and then multiply 9 by itself, 81, and then you multiply 81 by itself, which is like 3 to the power 8, and then you multiply that by itself, 3 to the power 16, multiply that by itself, 3 to the power 32. So which means you can compute this in 5 operations. And then we also need to multiply 3 to the power 35 by 3, 6 operations. So you see, like, we were able to multiply it by, obtain the final result by only using 6 operations, which is significantly fast compared to this one. So the log base 2n is stemming from the fact that in every operation, we basically half the power of, in every 2 operations, I should say, we half the power of n. So we start off with n to the power 33, and then after 2 operations, we are now looking at n to the power 16, and after another 1 operation, we are looking at n to the power 8. So basically, like, at every turn, like every operation, we just half the power of n. So we keep doing this until we reach 1, which is straightforward. So if you notice, this is basically like we're trying to identify which power of 2, basically, like, because we are halving at every step, which power of 2 is larger than n is the answer that we are trying to look at, which is essentially the same as log base 2n. So that is how log base 2n becomes the time complexity of this. I hope that's clear. Once again, I will try to see, I will switch back to the list of problems. Yep. All right. Is there any books that you can recommend for algorithms and data structures? Yes, there is the standard handbook. There are two books that I would like to recommend. One is Introduction to Data Structures and Algorithms. Let me see if I can find the book here. Maybe I'm misremembering. By the way, can someone confirm that you can see my screen?
Yes, sir. We can see.
Okay, nice. Let me try to see if I can. Okay, this is the book that I was referring to. Yeah, it is actually Introduction to Algorithms by a bunch of folks, and it's really good. It has some details about the inner workings of most of the common algorithms. And then there is this competitive programming handbook. Yeah, this is, yeah, if you just Google it, the first result will take you there. This is also a very good handbook, which has like, this is basically assuming that you are coding in C++, but to be honest, the language doesn't really matter. Once you are good at a particular language, you can easily transfer that to a different programming language. So yes. And then moving on to the next question. How useful programming language skills in electronic and automation field. I cannot give you more details because I'm not an expert in the domain, but generally speaking, having a good understanding would help you to easily simulate a lot of things by automating them. So rather than like having to work out a lot of computations by hand, you can just start writing scripts to compute them efficiently in general. But if you want to really understand how actually useful it is, you would need to speak to an expert in the domain. So sorry that I cannot give you a better answer. How to become a power engineer or any electronic and network field in Google? We should do MSc in relevant field to get that opportunities. Once again, like this is not exactly my domain, but I'll try to provide you a general answer. So if you are trying to apply for Google, it is generally good to have. MSc is a good to have, but it is not mandatory. Sometimes you can even directly apply from your bachelor's, but obviously the chance of getting selected or being interviewed is higher when you have an advanced degree. So yeah, that is all the information I have on it. So definitely do keep in touch with the recruiters by applying to all the interesting opportunities that you see on the Google Careers website. That would be a way to ensure that if you meet the bar, you get an invitation for an interview. That said, it's up to you to like improve your skills and demonstrate your performance using all the other available means, such as like publishing in the conferences and stuff like that, so that you get the attention when the folks look at your CV. And also like taking part in competitive programming competitions is also a good way. Me personally, I benefited a lot. I actually got the invitation for the interview based on some of the performances I had during my undergrad. So if you manage to perform really well, that could really benefit you in that front as well. Okay, and the next question. Oh, any resources to practice programming competition problems? Yes, there is a lot. So I can try to give you some of them if you can take notes. I'm pretty sure you guys are all familiar with HackerRank, right? Which is a which has a bunch of like problems and sometimes even tutorials that you can read. So that is there is another set of platforms similar to HackerRank that you can use to practice and enhance your skills. One comes to mind is that this timers.ru is the website where most of the Russian and Eastern European competitors practice on. So basically, you would need to maybe you don't even need a account. You can just access the problems. It has a very large problem set, basically coming from the Russian regionals. The problem set is really rich. We have a varying range of difficulties in these problems, and the test cases are also super strong. So it is unlikely that you will get your solution accepted unless it is accurate. So you don't need to worry about that. And there's a range, large range of difficulties as well. And if you want like extreme difficult problems, you can find them here as well. And then there is another website called Code Forces. If you know, you can just like try to Google for all the programming competition platforms. Then you will be presented with a long list, and you can pick and choose the ones that you are interested in. And most of them hold like regular contests as well. So can you get the competition experience as well? Yep. Again, the next question is some insight into how we can improve mathematically in problems like this. For example, using Uh-huh. Factorization is something that may not come directly to our mind. Yes, I think that's true. I think uh, that particular case, I think the idea is trivial if you have enough experience in the domain. But the one of the concerns is that most of the Sri Lankan students, they typically do not deal with functions very often, right? Even in the A levels, we have some amount of functions, but we don't really use the techniques that are used to simplify the functions very often. So that could be one of the reasons. And obviously, a great way to deepen your insights is to learn more theorems and related domain knowledge. That way, like when you start looking into more and more advanced topics, these simple things will get more established in your mind, and then you will be able to very easily employ them. The particular domain, if you are interested in these particular aspects, is called generating functions. Let's see if I can find something. And also, every time you see a result like this, try to generalize this so that you can use it everywhere, right? So generating functions is a technique that we use in mathematics, which you can translate into programming, obviously, and basically gives you a way to come up with a simplified expression by. So it is a way to deal with. It is a very powerful tool. One usage of it is to deal with the series. What you need to do is you need to first start off by expressing the series in a polynomial form. In the problem that we dealt with, that is being done for us. They already like defined the Fibonacci polynomial there. So after that, like we use a series of functional operations to simplify that function, and thereby coming up with a very efficient way of computing the like largest terms or coefficients of that function. So if you're interested in that domain, definitely do take a look and try to understand the inner workings so that you can not only do this for Fibonacci for any series. If you can find the right functional expression of that series, you will be able to compute the nth term very efficiently. How to learn deeply in mathematics? That is a difficult question to answer. There is a very large number of domains in mathematics. My recommendation is to pick and choose a bunch of domains. Maybe like if you are looking at programming competitions, try to look into number theory, algebra, and then graph theory and combinatorics. These things might be very useful. And in order to learn deeply, it's the same way as you would do for any other subject. You need to read a lot of material and digest them so that you develop deeper and deeper insights, and you try to find connections between all the theorems. For an example, even when you are studying different domains of mathematics, some of the core concepts are interrelated, right? Um, for an example, the Pythagoras theorem, while it is being a part of algebra, there are some isomorphic theorems in many other mathematical domains. So try to find more and more connections. And like I said, first step is try to pick and choose a set of domains that is going to be useful for you. And then once you try to iteratively deepen your expertise in each one of these domains, things will start to fit together more, and it will be easier to develop intuitions about the things that you haven't seen. And then next question, how useful programming language skills like Python in, I think I am jumping between problems. Sorry about that. I think I addressed that earlier. Let's start from the beginning to see that I haven't missed anything. Yeah, I see that the same problems were repeated a couple of times. Okay, there is a question. That's great. Let me see if I can load it on my personal computer, if I can. I'm trying to paste an image here. I hope it will be large enough so that we can see. Okay, great. Yeah, we can try to. So okay, as usual, we can start off by looking at the limits and such. And also, like, feel free to unmute yourself and take part in the discussion so that we can collaboratively make progress on this. As you can see, there's a modulo, so the intermediate big numbers are not going to be a problem, right? Let's look at the constraints. Obviously, n is large, closer to 10 to the power 9. The time limit is strict, I would say, half a second, which means you cannot pass with a linear time solution. You would need something like log n, it feels like. Now let's go into the difficult piece of it. Right. K is 17, not too bad. 2 to the power 17 comes up to around 10 to the power 5, I guess. But finding the teeth element is a bit of work. I'm trying to understand what the expression means. Sorry, I'm super slow. This is 2 to the power k equals t. Basically, like you want a, I guess both the conditions apply. So please correct me if my understanding is not correct. So basically, like you want some periodic elements when you take the mod of, okay. So if we just like do this for the 0th term and output 2k space separated values where the ith of these values is equal to a. Okay, so we want to compute this value for all the t's for, okay, find everything. So for a given k, so we see that we can compute for all the k's separately because we need to output all of them, and 2 to the power k minus 1 comes to about, I think we estimated this before, right? Yeah, 128,000 ish. So that is a reasonable number that we can fit. And the problem here is that since we are computing around 10 to the power 5 numbers, we need to be able to compute a single value in about 1,000 iterations or less. Otherwise, it's going to be too slow. Let me try to better understand the sequence T. So K is fixed, so you have a power of 2, and it feels like you are only going to be interested at the evenly spaced by a period of the power of 2. Mm-hmm. right? When A is equal to 0, you are going to look at like exactly starting from 0, you are going to look at exactly 2 to the power k apart set of numbers all the way until n. Let's start off at k equals 0, which is going to be the largest sum. And wait, I guess I think a bit of problem is truncated. I guess you would need to solve this for a given like specified k and n, right? Which means k is fixed. Let's say like k is just 1, and then a0 is relatively. I mean, if k is 1, it's just modulo 2, like this becomes, and we understand that I mod 2 of k cannot be larger than 1, right? If k is 1, which means like all the terms larger than 1, we don't need to worry about them. But the other side of the coin is that you would have a very large number of terms to sum up to find a0. You would have all the even terms, and for a1 you would have all the odd terms, and for that particular case you can use the binomial expansion of 2 will give you the summation of both of them, and binomial expansion of 1 minus 1 equals to n would give you the difference of the first two terms, a0 and a1, and basically it would mean that each one of the a0 and a1 would come to about 2 to the power n divided by 2, right? So I think, yeah, in that case it's relatively straightforward. But yeah, as k grows larger, let's now look at the other end of the spectrum, where k is very large. K is 17, let's say. So in the case where k is 17, we see that we want to sum a bunch of things with a period of 2 to the power 17. So basically, like we have n divided by, n choose 0, and then n choose 2 to the power 17, and choose 2 to the power 17 times 2, and so on. Yeah, I'm starting to think that once again, like it would be great that if you can unmute and join the discussion.
Hello, I'm the one who asked the question.
Yes.
So as I remember, the part that we struggled with was to find the n choose I, because the n can be very large according to the constraints. I think that was the part that we struggled with.
I see.
Yeah.
Like specifically a single n choose I or the summation itself? The summation seems like. Yeah, I see your point. Yeah, finding a single n choose I is also difficult because n is super large. The standard techniques like the Pascal's triangle definitely doesn't work. If you're familiar, I believe you might be.
Yeah.
Given that, yeah, this problem itself speaks to your strength. Yes, I think another aspect is that you can try to find the maximum powers. So there is this idea called so if you expand the n choose r, it's going to end up becoming like n factorial divided by I factorial times n minus I factorial, right? So there is this idea that you can find the maximum prime power that the numerator can be divided by, and also the denominator can be divided by. So if I am to add a little bit of details here, so I'm going to express, sorry, it is doing the auto capitalization for me. So this is what we have, right? So let's say like for all the primes that n is divisible by, I think that too might not work here because you would need all the primes all the way up to n. So are you familiar with this idea as well? Basically, like we try to find for all the primes that is up to n, we try to find the prime powers of the numerator, and then we also try to prime powers that the maximum prime power of the denominator, and then we try to, using these two, we try to estimate the maximum prime power in the result, and then we multiply them all to produce, for example, like let's say like we're trying to find 10 and 5. Right. We try to find the maximum power of, let's say like for prime 2, we try to find the maximum. This idea definitely doesn't work in this case, but I will just explain the idea anyway, right? So we will try to find the maximum power of 2 that divides 10 factorial. That would be like 10 divided by 2 plus 10 divided by 2 to the power 2. And we keep adding the sum until the power of the prime exceeds the number. So in our case, it would be up to this, right? Yeah, sorry, this is 2 to the power 3, not 2 to the power 8. Yeah, I think this comes to about 7, I say. Oh, sorry, 8. Sorry. Yeah, and we do the same for denominator, and we can use the same idea as here. So basically, the idea here is that if you expand the factorial of 10, right, every term that is 2 apart will be divisible by 2, right? Every term that is 2 squared apart is not only divisible by 2, but in addition also divisible by 4, right? So this is the idea that we utilize here, and we similarly do for higher powers as well, which will give us the maximum power. And we can similarly find the same number for 5 and 5. And then that way, like we can estimate the power of 2 in this result. We similarly extend the idea and compute for all the primes, and that will give us the prime signature of this particular number. And then we can use the prime signature to produce the actual number or some modulo of it. So, but in our case, the concern is that n is super large, which means you would need all the primes less than n for this approach to work. And computation of the primes is also relatively expensive. If you use a sieve of some kind, it would be close to something like n times square root of n, right? To compute this, maybe slightly more faster, but even linear time is not good enough in this particular case. So that is out of the question as well. So which makes me think that we would need some kind of a simplification for this before we just directly compute them. For an example, like we already examined the case where k is equal to 1, right? We were able to express the terms as powers of 2. And powers of 2 we can compute very easily using the fast exponentiation we just glimpsed today. So we may need to generalize that idea. And then even for like k values larger than 1, we might be able to produce some form of a simplification where we express the term in terms of the summation of some powers of 2, hopefully. Yeah. Does that make sense?
Yeah, I understood that.
Yeah. We can also like try to see, I think typically how I would approach is that we see that for k equals 1, it's trivial, and then we plug in k equals 2, basically like every term is now 4 apart, right? We have the like n choose 0, n choose 4, n choose 8, and stuff like that, right? I think an interesting property here is that all the terms, all the resultant terms, every time the summation of all the terms will be 2 to the power n, right? Because it features all the terms between 0 and n. And then in the first case, we use 1 minus 1 to the power n to get the alternating terms. And similarly, we might be able to use complex numbers to good effect here to produce the other terms. For example, like if you do 1 plus I to the power n or something like that, it will produce like a combination of different terms there, if that makes sense.
Yeah.
Yeah. And if you change the sign of the I there, the resulting terms, if you try to compare, basically like what I'm trying to get at is that you can use the 1 plus I to the power, it might even need to go even further than square root of -1, maybe like nth root of -1 to the power n, and then changing the signs, or if you think in terms of complex numbers, basically like left-hand side would be the complex number with the magnitude 1, but with changing angles. In the first case, the angle would be 180 and 360 to the power n, which will give you two equations which feature two separate terms, right? But for larger k, the angle would need to be in smaller increments, like 360 divided by 2 to the power k, ideally. And then as you increment the angle, you will come up with multiple equations on the right-hand side, which is a combination of the terms that we want to find. And then we use an equation solving mechanism to arrive at the final answers. Basically, like we get a bunch of equations which has these terms, right? And the left-hand side is just a power of a complex number which you can compute efficiently, and the right-hand side would be combinations of the terms that we want to compute, and then we can just use a matrix inverse or something like that. I wonder if we can even invert a matrix as large as 2 to the power k here, because that might also be too large. But in general, the idea that I'm trying to utilize here is that left-hand side, a simple complex number to the power n, and right-hand side, a bunch of equations that you can write using the AIs. And then you solve a series of these fine AIs. My concern here is that you might get 2 to the power k equations there, and in order to solve them using let's say matrix inversion might not be ideal there. But yeah, there might be some tricks around, like finding some of the simpler equations and then solving them and then using the results. Basically, like you might be able to solve the set of equations faster than n cubed, if that makes sense. I mean, this idea obviously could be wrong, but that is the direction that I feel like, because it doesn't feel like you can compute n-choose-Rs of this magnitude under this time limit.
Yeah, thank you for the ideas. I think we could try to follow that direction. Thank you very much.
All right. Yeah. I can also take a closer look and maybe like communicate with the organizers if I can find a different idea that works for this. Yep, excellent. Thanks a lot for giving a very challenging problem. This is indeed feels like a difficult problem. And coming back to the chat, can you give suggestions for first-year students for their career? I mean, what did you suggest? If I was in first year, yeah, take part in programming competitions and try to learn as many algorithms, and basically like it generalizes to everything. Find an area that you are passionate about and then try to deepen your expertise in the area. And once you become an expert in a particular area, it will definitely pay off after you graduate. So if you're in the first year, my recommendation is don't worry too much about the about your careers after graduation. You're just in first year, you are just exploring everything. Just explore as much as you can and try to find an area that you are passionate in, and then focus. Later on, you can start focusing more and more into that. Yeah, I think with that, yep, I think that was okay. There's more. Yeah, sorry about that. I think I'm seeing two versions of chat, and one of it doesn't have all the problems. So are there moments where you have to double log to reduce the processing time? Log of log. I think yes, there definitely is. Let me see. I cannot think of an example out of the blue, but basically, like it would mean that the computation inside of that it has to be also logarithmic. So yeah, I don't have an example off the top of my mind, but yeah, if you try hard enough, I'm pretty sure we can find a case where you would need log of log. Yeah, basically, like the way to search for something like that is that we understand the usage of algorithms where the complexity is log n, right? So within each log n, the operations need to also have a similar structure. Basically, you can think of it as two dimensions of the same problem. Yeah, but I obviously see it's very rare. I would say I don't recall. I mean, log n squared is relatively more common. Basically, like if you have two independent dimensions which you can apply the same ideas, then it's like log n like whole squared or log n times log k. But log of n is relatively rare. I'm sorry, I cannot think of an example off the top of my head, but I'm pretty sure if you work hard enough, we can try to find one, or maybe like we can just search Google. Yeah. Okay, moving on to the next question. Sorry that I cannot provide you with an adequate answer for the previous one. My question is a bit unrelated to competitive programming. Do you have insights, views on the area of making dynamic programming algorithms differentiable? I have this as a way of giving neural networks, making DP algorithms soft. Interesting question. Yeah, I'm not sure this is a topic that we can discuss in a matter of minutes. It is going to be a lengthy discussion, and we can definitely follow up if you have the interest. Feel free to directly reach out. And yeah, it seems like a very interesting domain. But for competitive programming, that it could be useful. There are some like insanely difficult questions that are featured sometimes. But I guess for the audience today, before we get there, there's a lot of groundwork that needs to be done. So I will not spend a lot of time discussing an intricacies of a like very fine domain here. So definitely reach out to me personally. I'm happy to discuss further. Next question, how old are you when starting programming? I think about the same age as most of you guys, just after joining the university. That is when I started programming, maybe 19 to 20 years old. That mod value is prime, might be useful. I guess you're referring to the problem that we are discussing right now. Yes, prime mods are useful in computing the mods because mostly because you can use the Fermat's little theorem to find the inverse. So if you notice in the previous one that we solved, the modulo value was not prime. It is the factorial of 15, they say. So it is not prime, meaning that every time you need to invert, it's a bit of work. Sometimes you might even need to use the Chinese remainder theorem. But in this problem, mod value is prime, which makes it very convenient to compute the mod values. Using Fermat's little theorem, we can easily compute the inverse. Like, for an example, the inverse, mod inverse of a particular number would be the same as that number raised to the power modulo -2, because we know like that number raised to the power modulo -1 is exactly 1 using the Fermat's little theorem. So yeah, that will help us definitely. And also, if you're referring to the fact that this particular modulo a number has a bearing on simplifying the equation, that is also in some of the problems that is a possibility. I do not want to exclude that as an option, because I also obviously don't see all the possibilities in this problem. But I really don't think that it is going to have a bearing on simplifying the equation here. Mostly because like this prime number, if it has a special form, maybe it is useful. Maybe like, yeah, like you pointed out, we can try it out to see if it has a special form, like if it is a power of 2 minus something or something like that, we might be able to use it to good effect. Another trick is that you don't, let's see, if you are trying to look up numerical properties, rather than doing it with a pen and paper, you can just try the number out in Wolfram Alpha to see like if it will give you any interesting properties. Says the number is odd, and the number is obviously sum of squares. Yep, the representation is a bit interesting. Yeah, it could be an idea as well. Basically, like one idea is to use that to try and eliminate some piece of the equation here. Basically, like every time, instead of computing all the n values, you try to prove if a particular set of numbers larger than 2 to the power k, we don't really need to care about them or something like that using the mod. But I am a bit worried because it has like 119. If this was like 2 to the power 23 plus 1, that is definitely a great result that we can work with. Even with this, it might still be useful. Yeah, that is, again, one avenue that you can try to walk down to see if it helps. Basically, the idea should be generally like, the general idea of revolves around simplifying this. That is pretty trivial. How you want to simplify this, one idea is to like make sure that you can truncate a piece of this summation by using some bounding logic. Basically, like if you can prove that the concern here is that you cannot really bound it because we are not. I see. Maybe yeah, maybe like we can revert back to the same idea as before, finding the prime powers, and then yeah, my concern here is that this number is prime and it's super large, so we might be able to get around numbers that are, yeah, yeah, basically my personal 2 cents, I don't think that we can find this to good use, but obviously feel free to try. My intuition could be wrong. That's a great point. Thanks for pointing it out. It might also be utilized to solve the problem sometimes, even though it is super rare to rely on a property, the modulo, to simplify the equation, but it is a possibility. Keep the options open. Yeah, especially like if it has a proper form, like some power of 2 or something like that. Yep. I think, yeah, that's the end of the list of problems. I guess, yeah, maybe I'll linger for a couple of minutes. Okay, yeah.
So now we have reached the end of our the final session of our Enigma 24 workshop series. So now let us all get together and thank our esteemed speaker, Mr. Hello, can you hear me?
Yep. Yes, we can.
Right. Okay, so let's all get together and thank our esteemed speaker. So once again, I need to make a kind reminder to you. The deadline for the registration for our the Crack the Code hackathon will be on the 12th, which will be on next Tuesday. So to all of the participants, if you still haven't registered, please make sure that you register before the deadline. That's actually the main an announcement which I would like to tell. And also, apart from that, so I hope that this session has helped you to gain some insight relating to the math-related coding concepts. So thank you very much to our esteemed speaker. Thank you for sparing 2 hours of your valuable time to educate all our youngsters.
Yep. Happy to meet with all of you folks, and definitely, like, if you have interesting problems and if you want to collaborate on solving hard problems, I'm open to collaborations. Do let me know, and one of you guys are interested in differentiable DP as well, feel free to reach out. I am more than happy to continue the discussions. Yeah, thanks again.
Yeah, let's do that. So to all the participants, now the session has been wound up, so you can leave the meeting.